This is question 8 from the SACE Stage 2 Physics course companion from subtopic 3.2 particle wave duality. Here we have light with a wavelength of 540 nanometers incident upon a metal surface which has a work function of 2.1 electron volts and a stopping voltage of 0.18 volts was measured. We need to use this data to determine a value for Planck's constant. So here we're using the relationship. That doesn't look quite right. Using the relationship E K max equals HF take W. EK max we can calculate using the stopping voltage. The stopping voltage multiplied by the charge of an electron gives the maximum kinetic energy. So this is calculated like that. The frequency we can determine using the wavelength. So here we're just using the rearranged version of the wave equation. And the work function, we've got it in electron volts, but we can just convert that into joules. That's easy enough. After that, we will rearrange this formula, substitute the values, and we should have a value for Planck's constant. So first let's work out the maximum kinetic energy. EK max will be EVS, which is the charge of an electron, multiplied by 0.18, the stopping voltage, and that ends up being 2.88 times 10 to the power of minus 20 joules. Our frequency is V on lambda, which is the speed of light, divided by 540 nanometers, and if we substitute that into our calculator we get 5.56 times 10 to the power of 14 hertz. And finally our work function, 2.1 electron volts goes to 2.1 multiplied by the charge of an electron to turn it into joules, and that ends up being 3.36 times 10 to the power of minus 19 joules. And now all we have to do is substitute these values into our rearranged version of the photoelectric effect formula. So EK max is HF take W, therefore HF equals EK max plus W, and finally H equals EK max plus W all over F. And now we can substitute those values in. EK max was 2.88 times 10 to the power of minus 20 plus our work function 3.36 times 10 to the power of minus 19 all over our frequency 5.56 times 10 to the power of 14 hertz, and we get 6.57 times 10 to the power of minus 34 joule seconds of Planck's constant, which isn't too bad. The real value should be 6.63. We've got 6.57. With an experimental error, that's probably okay. And that's it. There's not really much to it. A lot of conversions here and rearranging, but otherwise the question itself isn't too difficult mathematically. You just need to make sure you've got a good conceptual understanding of what's happening so you can respond to a question like this.